Hello ladies and gentlemen, and welcome back to Prospect Charter School's Algebra 1 course. Today we're going to be going over section 4.3, Writing Functions and Function Notation. So today we're going to be delving into the dark depths of mathematics, to the place that most people find not fun. I don't know why they don't find it not fun, but some people don't. And that is word problems. But you see, something that you should know is that word problems are the bridge between mathematics and the real world. You see, you never are given a simple equation in life. You're always given information, and then it's up to you to figure out what to do with that information. Sometimes you're given information like, George really thinks that Sally's hot and wants to ask her out on a date, but Sally doesn't like George because George is a macho guy that doesn't really ever try on his homework, and she's the kind of girl that likes nerds. Yes, I'm dreaming. But anyway, word problems are the bridge between math and the real world. They are how we go between the information that's given to us and how we can use that to predict what will happen, which is when George goes to ask her out, she dumps him and says no. So that's what we're going to be doing today, except that instead of with George, we're going to be working with a young lady named Tasha. Now, let's say for a moment that Tasha is babysitting on the weekends. And because it's not minimum wage and it's under the table, tax-free, she charges $5 an hour for babysitting. Our job is going to write an equation that allows us to calculate Tasha's pay. Well, this is actually a really easy one. When we're dealing with word problems, it's good to just derive the information from the word problem and look for the numbers that are given. Because a lot of times, all you really need are the numbers and the units, and you can use a cool trick called dimensional analysis, and with that, be able to write your equation without really understanding what's going on. It's a very, very powerful tool. So on this case, we know that we are given a rate, a number is right over here, and I will highlight it for us, $5 per hour. So I know that's a given. I know I am given that the rate or pay is $5 per hour. And there's nothing else there. So how can I calculate what her pay is going to be? Well, I know that this is a rate, and it has a per unit time and a monetary unit. Since I know it's pay, usually you get paid in dollars, not in hours, because being paid in hours would be weird. At least for us, we use dollars in America. So I know that in the end, I want to have dollars. So what I would do is I would create something called the railroad track method. And it starts with this nice little horizontal line and then a vertical line separating each one of my dimensional changes or changes in units. So this is going to be the thing that represents a unit change. Represents. I hope to God I spelled that right. All right. So I know that I'm given $5 per hour. So it represents a unit change. So I know I'm given $5 per hour. In the end, I want to be left with just money, just the dollars. So how would I go about doing that? Well, to do that, I have dollars and I have hours. I need to get rid of hours. So to get rid of hours, I would have to multiply by a fraction. Now, I don't know how many hours Tasha's getting. So if I don't know the value of something, being a mathematician, I put in a variable that represents that value. In this particular case, I'm going to use x, because x is the number of hours that she will be working. And it doesn't care how much she gets paid per hour. It just cares that that's how many hours that she worked. So we can say that the x is an independent variable, and the independent variable represents the number of hours worked. Now I have a rate of $5 per hour, and my pay, or Tasha's pay, depends on how many hours she works and how much she gets paid per hour. Now, how much she gets paid per hour is static. It's stuck at 5. It's a constant. While the number of hours that she works is a variable. So my equation is going to be y, which is the number of dollars that she gets paid, is equal to 5, because that's the number of dollars per hour that she gets paid, and then x. The reason why I know this works is because here in my dimensional analysis, when hours are on either side of our horizontal line, or if any unit is on either side of the horizontal line, they cancel each other out. So hours cancels with hours, and we're left with dollars. So for this word problem, I would say y is equal to 5x, where the amount she gets paid is equal to 5 times the number of hours that she works. Now, I know some of you were able to figure that out within like half a second of me writing it down, but it's really good to be able to formalize your thought process. In life, a lot of the time, to be able to get through things that are very complex, you need to make your thought process a little bit more formal. After all, the human mind can only hold about 7 to 12 things, depending on how amazingly awesome you are at a time. So let's go on to the next piece. Now, the next piece is another word problem. And this piece is going to involve our good friend, Farmer Bob. Farmer Bob is selling broccoli at $1.25 a pound. However, he had to spend $7,000 in anti-vegan zombie equipment. To protect his crops. Write an equation that models how much Farmer Bob makes. I'm going to say selling broccoli because we have to be more specific. All right, so let's go through this guy. Farmer Bob is selling broccoli at $1.25 a pound. I think that's probably going to be important. He had to spend $7,000. Okay, I think that's going to be important. In anti-vegan zombie equipment to protect his crops. Sorry about that. Frog decided to jump in my throat. Poor French guy. Write an equation that models how much Farmer Bob makes selling broccoli. All right, so what do we do? Well, I'm going to write down what's given. So I am given that it's $1.25 per pound, and that something is costing $7,000. So I'm thinking that we're going to have the same kind of situation before, where we had the $1.25 per pound, and then we don't know how many pounds he's selling, so we're going to multiply that by X, and then pounds and pounds cancel. I'm left with dollars. Okay, so that part's good. I know I'm going to have a 1.25X, but what's up with the 7,000? Well, it says he had to spend. So if he's spending money, does that mean that it goes into his bank account? Well, no, it means quite the opposite. It means that it's coming out of his bank account, which means that if he doesn't sell enough broccoli to make at least $7,000, he basically worked for free, or worse, paid to work, which is kind of bad. So I know that this $1.25 a pound is how much additional money that he's going to make, but I have to subtract from it the costs, and the costs were $7,000. So looking at this equation, I would say that the amount of money that our friend Farmer Bob makes is equal to 1.25 times the number of pounds that he sells minus 7,000. And I think that's a really good equation. I think that would definitely represent the situation that poor Farmer Bob is in. It looks like he's going to have to sell a lot of broccoli. Fortunately, he probably made a lot of broccoli, because broccoli is a wonderful vegetable. Highly recommend it. In fact, if I could, I would probably eat it every day, just like I do radioactive bananas. Because if you didn't know, all bananas are radioactive. It's the potassium. Okay, so, excuse me, moving forward, let's say for a moment that we are a physicist. And if you didn't know much about physicists, they have okay, I'm just going to say phys. Physicists have a lot of equations that they have to work with. So when we're writing equations, we almost always say y is equal to, y is equal to, y is equal to, right? And sometimes we'll have y is equal to something like 2x minus 5, or we'll have y is equal to 1/2 x plus 3/2, or we'll have y is equal to 8x plus 15. Excuse me, sorry. Having some allergy problems today. So, when we're dealing with a lot of equations, sometimes we'll be told that y is equal to 7. And it will be our job to figure out where it came from. What does this y equals 7 mean? Where did it come from? Which equation did I use? Did I use the first equation, the second equation, the third equation? What was my x value? What was my input? What are the units for this 7? You know, all these questions will be going through your head when you're a physicist. So what mathematicians did is said, we need a way to better organize this data because we need to figure out where the heck this 7 came from. It's kind of like that really awesome book, Hitchhiker's Guide to the Galaxy, where they had a supercomputer working on a problem for like hundreds of years, and then they came up with the number 42, and it was like, okay, so what was the question? Maybe the question was, what's 6 times 7? We don't know. We forgot what the question was. So we need to be able to have our data organized. We need to be able to say, here was the question, here's the answer. Here's where I used it. So to do that, we created something called function notation. Now, function notation makes our lives a lot easier because instead of having this y equals 7 thing, we would instead have something that lets us know what we're dealing with. So for the first function, because function starts with the letter f, I think we're going to start with the letter f. We're going to name this function f. And then what comes next? Well, the next function would probably be named g. What up, g? And then lastly, we would have the third function, which we will call h. And what we would do is we would write out our function notation so that we know not only what the input is, but also what the output is associated with that input. So the way we do that is we say f of, and then we'll have something for its input. Now, if we don't know what the input is, guess what we're going to plug in? Well, yeah, x. When you don't know what you're talking about, use an x. And then we have the rest of the function. It says that 2x minus 5 is equal to y. So my function of x would be 2x minus 5. Now what about the g function? Well, again, we're going to have g of x, because we don't know what we're plugging in originally, is equal to, and then we have the wonderful fraction 1/2 x plus 3/2. And then we have h. And h, we don't know what we're plugging in, so this would be h of x is equal to, and then we have our function 8x plus 15. Now when I'm told that y equals 7, the y portion isn't specific enough. It needs to be changed. It needs to be changed to h of something. And that h of something is probably going to be -1. So how is h of -1 equal to 7? Well, first I go over to my h function, which is over here in that beautiful pink color. And we're looking at h of -1. So what we do is we plug in -1 to our x values. Everywhere I see an x, I'm going to plug in a -1. So now I have 8, then I have a -1 for that x, and then plus 15. Now what is 8 times -1? Well, that's -8. And what is -8 plus 15? You guessed it, that would be positive 7. So this way, not only do I know which function I got that 7 from, but I also know what input gave me that 7 as an output. Now let's try a couple of others to make sure that we're kind of getting this down. Let's say for a moment that I have f of 3. And I need to find out what f of 3 is equal to. Well, I go to my f equation, which is, right here in this beautiful color red, and I plug in 3. So I say f of 3 is equal to, and now everywhere I saw that x, I'm going to plug in a 3. So that's going to be 2 times 3 minus 5. Now, note how, even though this stuff looks like it's saying multiply, we really don't. It's saying the value of my function when my independent variable is blah, which is a big handle to say, hey, I'm plugging in this number and here's my output. So I'm plugging in 3, now I need an output. So I plugged in 3, 2 times 3 is 6, and then 6 minus 5 is 1. So f of 3 would be 1. Note how I don't try to solve for f. I don't divide both sides by 3. I just leave it as is. I just say f of 3 is equal to 1. The value of my function when I plug in 3 into the f function is 1. Now let's go to the g. Let's go with g of 4. Well, I'm going to go to the g function. What up, g? I plug in the 4 for wherever I see an x. So I have 1/2 times 4 plus 3/2. Now I know you guys aren't very familiar with working with fractions, but that's okay. Fractions appear with functions all the time. That's why fractions are friends, and so are functions. You can't have fun without function. So, or you can't have function without fun. I'm not sure which way that goes. Anyway, when I'm dealing with these fractions, I note that at the beginning my denominators are already the same, so I don't really want to change that. I want to keep them the same. That way my job will be a lot easier. So if my denominators are the same, I need to turn this 4 into a fraction of 4 over 1. Please note that 4 divided by 1 is still 4, so I didn't really change its value at all. And then I multiply across. 1 times 4 is 4, so I've got a 4 on top. 2 times 1 is 2, so I have a 2 on the bottom. And to that, I'm adding 3 over 2. Now, because the bottoms match, I can just add the tops. 4 plus 3 is 7, so I get 7 over 2. And 7 can't really be divided by 2, so I would leave it as is. I would say that g of 4 is equal to 7 over 2. Now, I know what you're saying, Mr. O'Neill, shouldn't that be like 3.5? And I say, well, technically yes. Technically yes. However, if I turn this into 3 1/2, and then I want to do something like multiply it by 4, how do I go about doing that? Well, the first thing I do is I turn this 3.5 back into 7 over 2, and then I can multiply by 4. So what's the point? Why would I want to make more work for myself? Why would I put it into a format that if I wanted to add 4 1/3 to it, I would have to turn it back into this kind of a format before I could do anything? So I'm the kind of guy that says, let's not make more work for ourselves. Let's leave it as 7 over 2. So g of 4 is going to be 7 over 2. All right, and that's it for today's lesson. I hope this helps you understand where function notation comes from and why it's so important to get it down. So now it's time for your homework. Homework, everybody's favorite homework. I am not good at singing homework. All right, let's stop that before I embarrass myself further. All right, we're looking at section 4.3. Hashtags, math is awesome. Mr. O'Neill can't sing. Why on God's green earth is there a math disco dance that we're going to have to learn in Algebra 2? What is up with that? All right, section 4.3, and we're going to do numbers 3 through, I believe, 27. Let me double check. Yep, 3 through 27 odd. And for those that need to know, this is on page 253 in your textbook. All right, good luck and have fun.